Okay. In the previous class, energy efficiency. I told you this commercial efficiency will be useful only for the transformers which are having constant load, not for the transformers which are having variable load. See, in case of distribution transformers, there will be load variation for the 24 hours. Morning to evening, there will be load variation. Evening to next day morning, there will be load variation. When the load is continuously varying with respect to time, if you calculate the commercial efficiency or power efficiency, it will not give you a fairly good idea about the performance of the transformer. Because in case of commercial efficiency or power efficiency, what we do is we say 50% load, 75% load, or full load, something like that. But in distribution transformers, it's not so. In case of power transformer, if it is full load, nearly full load will be there for say 6 hours, 8 hours, 10 hours, or sometimes 24 hours. Whereas in distribution transformers, no such case can be found. Every 5-10 minutes, there will be change in load. Hence, if you calculate commercial efficiency or power efficiency for a distribution transformer, it will not give a fairly good idea about the performance of the transformer. Of course, it is always possible to calculate. It is not the question of just calculation. If you just calculate and keep it, the question is, what is the use? Will it give proper information regarding the performance of the transformer, regarding efficiency, is the question. So that will not be really useful. Hence, energy efficiency, which is also called all-day efficiency. You see, it is called all-day. That means the efficiency of the transformer with respect to one day, 24 hours. In 24 hours, how the transformer is performing with respect to efficiency is to be seen. That will give a fairly good idea about the performance of the transformers. Hence, energy efficiency or all-day efficiency is defined. So we'll see. As the name itself says, energy efficiency of energy, not in terms of watts or kilowatts. For power efficiency or commercial efficiency, we have output power divided by input power. Both are in watts. That we simply write output divided by input, or output divided by output plus losses. So only you have x into V2I2 cos phi 2 divided by x into V2I2 cos phi 2 plus Pi plus x square into PCU or PC. That's our formula. In case of all-day efficiency, which is also called energy efficiency, it is defined as output in energy, in terms of energy, not in terms of watt. It is in terms of watt hour. Always time is multiplied by to the power. Power into time is energy, you know. So output in energy divided by input also in energy. So all terms has to be represented in terms of energy only. Okay. So all day efficiency is output in kilowatt hour divided by input in kilowatt hour. So that is output in kilowatt hour divided by output plus losses in kilowatt hour. Output is also in kilowatt hours. Losses are also in kilowatt hours. Please remember, it's not in watts. Watt hour. Many times some students will commit that mistake. Output, they will keep it in energy. Losses, they will keep it in watts. No, that is not permitted. That is wrong. Whenever you are performing any operation, on any of the parameter, constituent units, you can add voltage to voltage, not voltage to current. You can add watts to watt power. Watts and current you cannot add. Any operation between two parameters should have the same unit. Okay. So rupees and rupees you can add. Rupees and paise you cannot add. 10 rupees, 10 paise. 10 rupees plus 10 paise cannot be 20 paise or cannot be 20 rupees. Something like that. That I hope you know. Okay. We'll now look into the numerical problems. That's all. That's all for energy efficiency. See, output in kilowatt hours. Kilowatt into number of hours. Okay. Then losses in watts into number of hours. For so many hours, what is the loss? So many hours, what is the output? Okay. Totally, it is for 24 hours. Total output is for 24 hours. Total input is also for 24 hours. So total losses is also for 24 hours you have to calculate. Okay. Now based on that, we will try to solve some numerical problems. Okay. A 15 kVA 2000 bar 200 volts transformer has an iron loss of 250 watts and a full load copper loss of 350 watts. During the day means 24 hours. Okay. It's not just daytime. During the day, it is loaded as follows. Find the all-day efficiency of the transformer. So the table gives you the details of the loading. For 9 hours, 25%, 0.6 power factor. Hamsa R, I am hearing noise from you. Please mute your microphone. See, what is that you are doing? Every day I have to tell one or the other person, mute the microphone, mute the microphone. What is that? Why don't you mute your microphone as soon as you join the class? This table gives you the pattern of load on the transformer. Okay. So 9 hours, 25% load, power factor is 0.6. 7 hours, 100% load, power factor is 0.8. Next 6 hours, 75% load, power factor is unity. Next 2 hours, there is no load on the transformer at all. Transformer output is switched off or there is no load connected. Try to understand. See, the load is also changing, power factor is also changing. That is the reason why we go for all-day efficiency or commercial efficiency. All-day efficiency or efficiency in case of distribution transformers. Please note, it's applicable only to distribution transformers, not power transformers. Energy efficiency or all-day efficiency is applicable only to distribution transformers, not to power transformers. Okay. So number of hours, you should note, sum of the number of hours should be 24. Totally 24 hours. Okay. If by chance some hours is missing, then you can assume that this is for no load. Suppose this finally says at the end 2 hours, no load, percentage load is 0 and no power factor. Okay. So by chance he says 976 only. That comes out to be 22 hours. Remaining 2 hours is no load. You can assume. By chance in some numerical problem, such a loading pattern comes by chance. Then you should say, number of hours of load given is only for so much hours. For example, here 22 hours. Remaining 2 hours, it is assumed that the transformer is on no load. See, these are all the engineering ways of solving problems or doing things. Okay. So now, based on the data given, we will try to solve the problem. Okay. He has given iron loss is 250 watts and full load copper loss is 350 watts. Okay. We know iron loss is constant loss and the copper loss is variable loss. Copper loss is variable loss. Okay. Iron loss is constant loss. So it will not vary. Hence, we can find out the iron loss for 24 hours. That is energy. The loss in terms of energy for 24 hours. See, that is 250 watts. That is 0.25 kilowatts into 24. 6 kilowatt hour. 6 kilowatt hour. I hope in electrical science in first semester you have studied about some electrical energy, then charging of energy, etc., etc. In your home, whatever the bill, electricity bill you get is in terms of kilowatt hours. So much of energy is being utilized by you, not the power. So here 250 watts into 24, in that case you will get watt hours. But you use kilowatt hour because 1 kilowatt hour is 1 unit of energy. That is the commercial unit of energy for measurement. In your home, if you see the electricity bill, it is in kilowatt hours. That is 1 unit. Charging is also for in terms of 1 unit. 1 unit, so many rupees. 4 point something, 6 point something, etc. So you have to look into that. So remember, it should be in terms of kilowatt hours, not watt hours. Okay. Now you see. Next, copper loss. Copper loss for 9 hours. See, first 9 hours it is 25% load. Copper loss is for 9 hours. So for 9 hours at 25% load. 25% load. That is x square. 25% load means 25% of full load. Full load is 15 kVA. Okay? Into 0.35 into 9. That will give you 0.196 kilowatt hour. This is 0.25 square, okay? It's not 0.252.